Okay, so it's a pleasure to welcome Andy Odesky from Princeton, who will tell us about algebraic integers of bounded height and given Galois group.
Thanks for the invitation to speak. So hopefully natural enough problem that most people will find it motivating. So I'm just going to start by setting some notation. G is going to be a transitive subgroup on n letters, and the bounding function that we want to study. So x here is just some real parameter that's getting large. H is pretty much any natural height function that we might consider on algebraic integers. So there will be a few of these we'll consider. And we want to talk about a number of algebraic integers which have height x, and Galois group of its minimal polynomial is G. So I'll just talk about some known results on this, on the asymptotics for this quantity. So the first one to mention is if we sum over all transitive subgroups, so this amounts to talking about algebraic integers with fixed degree. And here, this result was proved for the Bay height, which is one natural height to use for algebraic numbers. And it's known not just asymptotic, but even the leading form of the asymptotic. So, the leading term is going to look like this, and this is actually a explicit constant plus some error term. Error term's not too important for us. So this is a result of Chern-Waller from 2001. At least they didn't state it explicitly, but Widmer pointed out that it follows the results. So that's where we sum over all the Galois groups, but you might ask for specific Galois groups. So for P prime and cyclic groups of order P, Unk, Oliver, and Thorne in 2020 proved that Simonyi PZ, this time using a different height. So this is called coefficient height. By coefficient height, I'll put it here. I just mean.
Can you talk us through this first result for n equals 2?
Sorry?
This first result for n equals 2. I'm just trying to understand how the normalizations work.
Yeah, so it's just the normalizations with the absolute Bay height.
So I'm counting quadratic like integers and quadratic over z. Is that right?
Yes.
How do I get x to the fourth out of that?
Well, there's a normalization of 1/2 because it's degree 2. So you divide by 1/2 in the Bay height. So you expect x squared, but it gets multiplied by 2.
And why would I expect x squared?
So it's just because of how the Bay height's defined.
Can you remind me how Bay height is defined?
I don't really want to right now. Maybe afterwards I can tell you. It's just, it would take a lot of time. So I'll tell you this one though. It's simpler. So if we have the minimal polynomial of the algebraic integer, then we just take the max of the coefficients. So for this height function, Lemke, Oliver, and Thorne showed just an upper bound. This was x 3 minus 2 over p of p minus 1 x. And this was later improved by Bhargava fairly recently. And for the same quantity, And you show that it's actually big O X squared. And that was in the course of proving Van der Waerden's conjecture, which I'll also mention here. So if G is not all of Sn, then Barger will show that the asymptotic you have, again, for the coefficient height is big O of x to the n minus 1. So that's more or less what's known. There's not too much known about this problem. For specific groups, pretty much just have upper bounds. So we'd like to know more about the leading term, maybe even leading constants. So I want to describe what might be the first approach to this question, where you partition the algebraic integers by fields with Galois group G, and then you count the integers in each field. So this approach turns out to run into some issues in the general case. So just for explaining this approach, I'm just going to assume that G is Z mod P. We also need to assume that P is at least 5. It's 5. So K, BQ join alpha, Galois group G. Okay, it's ring of integers, discriminant K. And for the height function, for this approach, we use the Minkowski height, by which I mean non-equal norm on Minkowski space. So an elementary application of a basic result from geometry of numbers, Minkowski's second theorem on successive minima, says that if you have an algebraic integer, which is not an integer, and its Minkowski height is bounded by x, then the discriminant satisfies a bound that's less than 2p minus x to the 2p minus 2. And here we really use that G is Z mod BZ. So the reason why this is useful for this approach is because if we want to, well, now we know that since we're counting algebraic integers of bounded height, we only need to count over fields with bounded discriminant. So this counting function is here. We're going to sum over fields of bounded discriminant. Inside of each field, we want to look at those algebraic integers with almost x, which also generate the field. So this just forms a lattice. We're counting elements in a lattice of bounded height. So this is asymptotic to x to the p divided by the covolume, just the square root of the discriminant. So this whole sum is asymptotic to x to the p times sum over fields, Galois group G, and the discriminant, and those x to the 2p minus 2, 1 over the square root of the discriminant. Now, here we can actually understand this sum thanks to a conjecture of Malle that's proved for cyclic groups of order P, or abelian groups more generally. So Malle's conjecture implies that this sum actually converges as x goes to infinity if p is at least 5. So here we do need that p is at least 5. So, like I mentioned, Malle's conjecture is known for abelian groups by Wright, or even earlier by Monkey. So what this argument shows is that, at least for cyclic groups of prime order, we know the form of the leading asymptotic, and this is some kind of a formula for what the constant is. but it's not a very good formula. We'd like to actually know what this leading constant is. This is not really something that we can evaluate. And we'd also like it to work for more general groups. So main result that I'm going to talk about today is just we're going to calculate this leading asymptotic for cyclic roots. And also give a formula for the constant. So to state the formula, this particular algebraic group is going to play an important role. So it's the unit group of G, which is defined to just be the units in the group algebra of G, which means that if I have any ring R, the R points of this group are just the units in the group ring in R. So for abelian groups, this is a very nice kind of torus, and it's just a quasi-split algebraic torus, a very nice kind of group. And it even splits over a cyclotomic extension. So another torus that we'll need is quotient of this unit group by the group itself, which is again another algebraic torus thanks to commutativity. So A, we write for the Adele ring over Q, and K for maximal compact subgroup. So we need to know a little bit about the arithmetic of tori. So thanks to some foundational work of Takashi Ono, we know that the level K automorphic quotient of torus, of any torus, has a fairly canonical splitting into three parts, three groups. So C here is a generalization of the class group. R is generalization of the regulator group. And we have this real vector space factor. So the class group is finite, regulator group is connected and compact. And we also need this this group, which is going to be the elements in the maximal compact subgroup, which are rational. So this is discrete, compact, so this is a finite group. So one more thing is I need to tell you what height function we're using. So to compute the leading constant, we actually use a particularly nice height function for this context, which is a particular height coming from the theory of toric varieties. So this was a height function which was introduced by Bodirev and Schinkel in the course of proving Meining's conjecture for toric varieties. We're going to borrow their height. But if you want to just think about it in terms of polynomials, this is equivalent to the following height function, which I'll call the root height. And it's similar to the coefficient height, but it's not equivalent to it. Kind of reflects the fact that the coefficients of a polynomial are not linear in the roots. So we extract roots to make it linear in the roots. So if you want, you can think about the statements with this instead. So that notation, state the theorem. So for the first part of the theorem, I want to state it for Z mod 3Z because it's actually kind of an exceptional case. And it doesn't really matter if we use toric height or the root height, they are equivalent up to a factor of root 3. So I'll just do it for the root height. And the result is that this is a constant times x cubed times log x plus, well, we actually get an explicit error term, but focus on that here. Where C3 is the following constant. for cyclic groups, more generally, n at least 5. So don't actually treat n equals 4, it's a little gap. Cyclic groups order at least 5. We do prove that the same asymptotic holds. Again, you could use root height or toric height here. So I'm just going to use toric. And again, there's a constant, and it's x to the n, and this is the leading term. It's a little low. And we proved an explicit formula for this constant in general. But for this talk, just to keep things simple, it's a little bit simpler if I'll just state the formula, and it mostly gives the flavor, but I'm just going to do it for cyclic groups or prime order. So E is at least 5 prime, and CP is given by this formula. Capital P. Okay, so these constants I'll define in the course of the talk, so to be defined. The first result, I should say, is joint with student. But an exceptional case, because it didn't fall under this method, 2023. And then the second part is solo work, combining work from 2024, which did most of the work, and then a little bit more in some ongoing work.
Expected the product of the primes?
Nope, yeah, not necessarily. Yeah, this factor ends up coming up out of the analysis due to like the singularities of a particular toric variety that'll come up later.
The Q's are prime in this problem?
Yeah. So one thing about our proof in the methods, well, I'm going to explain it for the course of the rest of the talk, but we don't use Malle's conjecture. Unlike the first approach, we actually count algebraic integers directly. So I'm going to describe the strategy, focusing on parts that I think might be useful in other contexts. Roughly, the game plan is that we convert the
heuristically motivate the exponent that you get without the details. Yeah, can we see why we get exponent n by some sort of?
Yeah, I think the first approach gives a pretty good heuristic for that.
Oh, okay.
Yeah, so I think that suggests that that's sort of what you might expect.
Okay.
Maybe even for other groups, but at least the justification for it seems to break down.
Why the log x or 3?
Yeah, well, maybe one reason is because this product actually diverges.
Okay.
If P is 3, yeah, I don't have a better reason.
Sorry, what is the exponent? I can't read the.
Oh, sorry, it's P minus 1 over 2.
P minus 1 over 2, thanks.
Minus P minus 1 over 2.
It's in the minus.
Okay, so I want to talk about a property of algebraic numbers, which is not focused on too much, called normality, which will turn out to be very useful for counting algebraic numbers in general. In this part, we are just going to take G to be a finite group, so this all works even if G is not necessarily abelian. So when you start counting algebraic integers or fields, you run into this issue, which is that there's no moduli space for G fields. And The reason for that is just that the category G fields is not closed under base change. You generally will get just an algebra. You do a base change. So you don't have a well-defined moduli problem. So the smallest class of algebras containing G fields, which is closed under base change, are what are called G algebras. So let's take little k to be a field. So a G algebra is a separable algebra equipped with a G action, faithful G action, whose subring of G invariance is just k. And a normal element in a G algebra is an element whose Galois conjugates is a basis. So the category of G algebras is better than G fields for counting. They form a stack. So G algebras represented by stack, BG. But we don't really like working with stacks. We want to work with a variety. So we'd like to have some other variety which is closely related to BG. And the strategy to doing something like this is to consider the problem not of G algebras, but G algebras with some extra structure. So for inspiration, you can look to a paper of Kunin from 2008, who was studying the related problem of fields with a fixed degree. So the process of adding extra structure is what's called rigidifying. And so Kunin rigidified category of commutative algebras of finite rank by adding some extra structure. And that extra structure was a fixed basis. So he considered pairs of commutative algebra finite rank together with a fixed basis. Then you get a nice variety that you can study to understand the thing that you really care about. So we're going to do something similar. We could just take G algebras with a fixed basis, but there's a better thing to do, which is reflecting the action of G. So every G algebra has normal elements. That's something you can prove pretty easily. And we're going to rigidify by considering K algebras, I'll just write it over Q, together with a normal element. And we'll say that two pairs are equivalent if there's some isomorphism of K algebras, which is G linear, and takes alpha to alpha prime. So it's not too hard to show. It's not formal, but it's not, we won't call it deep. It's called a proposition from some joint work with Julian Rosen, 2020, which is that G mod G, at this point, just a homogeneous space. This is an affine variety, and it turns out to be the moduli space for these pairs. In particular, if we're talking about just its rational points, sort of what we care about, then there's a canonical bijection that produces from each rational point of G algebra over Q and a normal element of that G algebra. Now,
Sorry, here you specialize to Z mod NZ.
no, still G is a finite group.
What is the script G?
The algebraic group of units in the group algebra.
Oh, I see. Okay, but It doesn't require for any group, okay.
Yeah. Yeah, so in general, by Schur's lemma over Q, it's like a product of inner forms of general linear groups, but it's still a nice group. Not it for us anymore. So one other nice thing about normal numbers is that they have an action of the rational points of this unit group. It's not too hard to show that if alpha is normal, then its translate by any element of this group is still normal. And in fact, this is actually a simply transitive action. And what this implies is that the property of being normal is a generic property. So if you want to do something for algebraic numbers, like count them, you can hope to just count normal numbers and hope that the non-normal numbers are just, there's not too many of them, and that's exactly what we do. And the thing you gain from that is that you can work with a set of numbers that has a lot more symmetry, namely the symmetries by this algebraic group. I think it's fair to say that study of rational points of G mod G is so far proven to be a fruitful approach to studying algebraic integers with a given group. So one way to make this a little bit better is that we can compactify this affine variety, which is important if we want to use heights. And it's simple and easy to describe. So G, we can think of as sitting inside of the regular representation, which is not compact, but we can add a point at infinity by just taking the direct sum with the trivial representation and then looking at the space of lines here. So we just get a projective space. This is the G equivariant map. And then we pass to the quotient by G. And this map here is G equivariant. And so this is the now compactification that we can talk about rational points on. And it's going to provide for us the theory of toric varieties when we assume that G is abelian. One difficulty, though, is that it has quotient singularities, which are obvious from its definition. That does make things a little bit harder, actually significantly harder. A little bit more about X. So there's also a natural divisor and X, which is defined over Z, such that if I have a rational point of G mod G, then this is de-integral in the technical sense, if and only if alpha is integral as an element of K. So we really can think of the problem of counting algebraic integers with given Galois group and bounded height as a integral Diophantine problem on X. So now let's assume that G is abelian. So this has two relevant consequences for us. So the first is that G mod G, which I'll call T, is a torus, algebraic torus. And the second is that X is now a toric variety, or Q. Basically, just by definition, it's a variety containing T equivariantly. And extending the action of T on itself. So we have this whole theory of toric varieties that we can now use. Since toric varieties are not exactly a standard number theory topic, I'll say a few words about them. So there's a well-known equivalence that describes algebraic tori over Q. So the category of algebraic tori over Q is equivalent to the category of lattices with a Galois action. Galois for Galois, where you take a torus and you map it to call it n of t, which is the z dual of its character lattice. And this equivalence extends to classified toric varieties as well. Where now we just have to equip lattices with some extra structure, so we need lattices plus what's called a fan, the Galois action. It won't be too important to know exactly what fan is, but you can think of it as just a collection of cones in the lattices n. It's a collection of cones in the real vector space n tensor R. And I'm going to write fancy little t for this because it's when it's coming from torus, it's canonically isomorphic to the Lie algebra. Satisfying some conditions, so closed under taking faces, and every intersection is a face of two cones is a face. So Malle-free and Schinkel studied toric varieties. They were one of the first general classes of varieties where Mining's conjecture was shown to be valid. And part of their method involved using what are called toric heights, which are actually a very simple natural notion. So their idea is to start with a line bundle on your toric variety. And this will give you some Weil height, some height defined up to equivalences, but they want to do something more. So let's take a line bundle that has an action of t. And their idea is to, instead of using the Weil height where you take the max over the coordinates, we're going to diagonalize the action of t on the linear system associated with this line bundle. It's always possible. And you essentially replace the coordinate functions with weight vectors in the linear system and then just compute the height the same way you normally would, but with those weight vectors. And the result of this is you get a nice height, which decomposes as a product of local heights. It's defined on the adelic points of the torus. And this construction works uniformly for any line bundle equipped with a t action, which I'll already just pick t. So we get this family of height functions. And from this,
I'm sorry, the point of this is that it's not just somehow up to a constant, but it pins down a specific line of the class.
yeah, exactly. So it's a nice height to work with. So for projective space regarded as a toric variety, the usual Weil height is a toric. Those coordinates are weight vectors. Okay, so from this we can form the height zeta function, which is just the generating Dirichlet series for rational points on the torus. And since we're interested in the d-integral version of this problem, we're going to also take into account the characteristic function of d-integral points. We just want to sum over d-integral rational points. So this defines a this is a multiple Dirichlet series on x, so S is here, and it converges . as is sufficiently positive in the sense of algebraic geometry in the effective cone. So in order to apply this approach of Body-Rev and Schinkel, we had to generalize it a bit because their approach was about rational points, not about integral points. And they assume that the toric variety is smooth. So our work, 24 work, it generalizes and builds upon their method in a few simultaneous ways. Basically the ones that I mentioned, so allow for integrality conditions. We can handle quotient singularities. And finally, we actually go a little bit further than they do in studying the height zeta function. So they computed the rightmost pole of the height zeta function. We actually compute an explicit formula for the height zeta function using some theory from the theory of multi-dimensional residues. So closest paper in this direction is Sare, Seek, and Donov, 92. Okay, so now I want to say a little bit more about their method. So they want to exploit the symmetries of the torus, and the idea is we're going to just apply sound summation, but not in the typical way. We're going to apply a multiplicative form of sound summation. I'll explain what I mean by this. First, let me sort of say it in some generality, because probably maybe some people haven't seen this general version. So if you have a locally compact abelian group, and you have a closed subgroup, all right, be checked or check for unitary dual, and a perp is going to be those characters which are trivial on A. So the general Poisson formula says that if f is an integrable function of B, the R measured, and the restriction of the Fourier transform of f to a perp is also full, then integral of A over A of f a b is equal to the integral over a perp of f Fourier transform I b b for almost all b. So typically, f is in its Fourier transform are continuous, so you can just take b to be the identity. It's a version more usually applied. So we're going to apply this to A being rational points of the torus and B the adelic points of the torus. So our function is just going to be the sum n of the height zeta function, and the result is that our height zeta function is expressed as an integral over characters of the adelic points which are trivial in the rational points. So this is the same thing as this automorphic quotient of the Fourier transform. This. And actually, it's a little bit better. So f is actually invariant under K. So actually, this is integral over that level K automorphic function. So thanks to Ono, there's essentially three factors of this integral to worry about. There's the part over C, the class group, R, the regulator group, and then also the real vector space. And really, the hard part is the real vector space. The non-compact part is difficult to handle. So that's where the residue theory comes in. So say a bit about that. So I mentioned that the toric height is a product of local heights. So in particular, the Archimedean component is very important for evaluating this integral. It's a function of two parameters. We have the line bundle, and we also have this unramified character on the real points of the torus. And this turns out to be a rational function with poles on hyperplanes, which are very simple kinds of singularities. So if we want to try and take residues in this higher dimensional setting where the singularities are hyperplanes, then we should be looking at flags. So for any flag in CR formed from these hyperplanes, we can make sense of the iterated residue of Archimedean height Fourier transform along the flag, where you start at the first subspace in the flag, take the residue will be a function on that first part of the flag, and then you iterate it. So what our work does is we introduce a notion called stability. For flags, the point being that only stable flags contribute to the pole of the height zeta function. So the property of being stable is very restrictive, so it cuts out a lot of flags. And the resulting residue can be more simply studied where we only sum over the stable flags. So I'm going to call this R of S, where we sum over stable flags and C R of these iterated residues. So this is now a rational function of S. S is now belonging to the line bundles not on X, but because we're in the Archimedean setting, it's actually a base change of X over R. And the fact that we've taken an iterated residue along this flag means we've essentially lost the variable in C to the R. And so there's a natural way of embedding that C to the R into the space. And so we get a rational function on this quotient vector space. Okay, so with this function, I can define the remaining two constants. Finish the statement of the main theorem. So just define one more bit of notation. So if I take that Lie algebra and look at its invariance under the decomposition group, this contains the total Galois invariance And this actually has a canonical subspace invariant, complement, which I'll call E0. And furthermore, E0, its dual, canonically sits as a subspace of this quotient space that the rational function over there lives on. So constants E sigma. The sigma here is the fan of the toric variety. It's going to be computed using the data of the toric variety. As you integrate over this subspace R of SAC, SAC is the element which corresponds to the anticanonical divisor. 2 pi 5 m. So this converges and just defines a complex number. It's actually a period in the sense of conservative type. And the other constant, C sigma, is just you evaluate this residual function at this particular element. The significance of this is that this is location. This is the location of the rightmost pole of the height zeta function. Any questions? Okay. Great. So I have a little bit of time. So I want to talk about. I want to talk about something a little unexpected that came out of this construction when I was looking at the case Mod3Z with Super-G, Bhattacharya. That's interesting. So we're going to take G as Mod3Z. It turns out to be convenient for studying the problem to do this particular normalization where we normalize by the trace. So this amounts to taking G and T and replacing them with their quotients. They have a direct factor of Tm corresponding to the trivial representation. And in terms of the moduli problem, this amounts to taking the normal elements and replacing them with themselves divided by their trace. So you can show if your normal trace is always a unit. So this makes sense. So they become normal and trace one. So this doesn't really entail any loss of generality. And it reduces the dimension of the problem by 1, which is convenient. So for Z-mod3Z, everything's going to be in 2 dimensions. So I'm going to draw for you the character lattice for the 2 tori G and T, where I've modded out by the direct factor. So it's most natural to write it as the hexagonal lattice. So the elements of the lattice generated by these 3 vectors, the outer part, generate the character lattice for G, and the rest is the character lattice for T. And the inclusion map here on the co-character lattice. Picture of the co-character lattices. So the map here on the co-character lattices is witnessing and corresponding to under that equivalence of functors or equivalence of categories to this the natural quotient map. And the Galois action is by reflection along this line, where the absolute Galois group acts via the quadratic character associated to that quadratic field. So quadratic field here. Now, it's easy to see that G, this group of units, is actually just isomorphic to the restriction torus. for this quadratic field. And as for T, well, it turns out there's actually another map besides this inclusion map that you can consider. And this map, I'm just going to take this element and I'm going to map it to this element. So there's a unique Galois equivariant map, which is an isomorphism, which sends this to this of these co-character lattices, eta. And that's a different map, which is actually an isomorphism. And it corresponds to a different map between G to T, which is an isomorphism. So this has the consequence that since G and T are isomorphic, we can look at their rational points. So on the one hand, we have the rational points of T, which, as we explained, are in bijection with Z-mod 3Z algebras. But there is a canonical bijection between this set and the Q points of G, which are just the non-zero elements of this field. So there's a natural way of writing down a bijection between these sets. It's not obvious at all. And I'll write down what the bijection is. So I'll state it on the level of polynomials rather than elements. So the characteristic polynomial of any alpha in this set will have trace 1, so the t-squared coefficient is -1. And I should decide first. So if I take the characteristic polynomial of an element in this field, then it has, let's say, trace t in norm n, and the associated polynomial is by this formula. That's the map in this direction. And in the other direction, if you have a polynomial arising as the characteristic polynomial of an alpha in a set, then it gets mapped to this quadratic polynomial. So that's the bijection, and it has a lot of nice properties where you can translate the properties of one polynomial into properties of the other, and it's not always obvious. So first off, maybe let me describe what kind of polynomials arise as characteristic polynomials of an element in that set. So it'll be a polynomial that either has Galois group Z mod 3Z, or it might not. And if it doesn't, then it has to split over Q, and it's not allowed to have a triple root. And on this side, we have any quadratic polynomial defined over Q with the property that it splits over this quadratic field. So here are some correspondences between these sides. So first you might ask, when does F split over Q? And it splits over Q if and only if there is some W inside this field such that Z is W squared over W bar. G will be irreducible over Q if and only if F is separable. So it has the same roots. The discriminants are related by this formula. And there's also some integrality conditions that I could write down, but that correspond to describing when f has coefficients in z. It's a little complicated. I'll just give an example and then draw a picture. So here's a example of a polynomial. And this turns out to correspond to this quadratic polynomial. So it's not the obvious answer that f is integral, that's not like g is integral. There's some non-trivial three-added conditions that have to be satisfied. So the picture I'll just draw is just a picture of the left-hand side on the complex plane. Draw it here. So those g's which are irreducible. So this is U3 the side of C. So g is irreducible means that the two conjugate roots of g are off of the real line. So those on the real line are when g is reducible, and so this real line is corresponding to those f's with the double root. And if f doesn't have a double root, then two rational points. Well, one of them is the alpha whose characteristic polynomial is given by the bijection. The other one is the same alpha, but a different k. It's actually the twist of k by the outer automorphism of z mod 3z. That's the conjugate point. And when you're a double root, that means you must split over q, and so you don't have a twist. So you don't have that same correspondence between conjugation and that outer twist. Okay, I'll stop there.
Any questions, Fran?
So I lost track a little bit at some point. So you set up all of this machinery. How did it apply the asymptotics?
Yeah, I didn't explain it fully, but there are some theorems. Tell me if this is not what you're asking, but there are some theorems that let you translate analytic properties of the height zeta function into asymptotics for the sum of the Dirichlet coefficients of the same bound. So basically what you need to do is understand the height zeta function well enough, in particular its pole, which I sort of mentioned a couple times, and that's why all these invariants of the pole keep coming up. And if you understand that pole well enough, then you can say like whatever you want about the asymptotic expansion of the counting function. Yeah, that I don't have anything new to say in that regard, so I didn't say much about it.
You mentioned that you could also get something about the error term. You wrote the error term, but you said I thought you said you had sort of better.
Yeah, so specifically for z mod 3z, we get a really strong result. So we compute the secondary term as well, and a constant for the secondary term explicitly. It's a lot worse than leading constant, more complicated than the first one. And then we compute an error term on the secondary term. So the secondary term really was proportional to x cubed, which was that error term that I wrote in the statement. And then beyond that, the next term, I think it's x squared log x. I'm not too sure.
Yeah. How explicit are these three constants? Like, can you actually compute them somewhere?
Yeah, I actually write down a formula for this one, and it's kind of nasty. I originally was going to state it and then decided it just wasn't worth it. But you can write it down, and it's just like some rational number. This one, I have no idea how to compute in general. Yeah, some period.
But it's something. So yeah, because it's obvious. This is an iterated residue. Okay, I see.
Yeah, some rational function.
But then you're integrating over all of what is
some real vector space. Yeah. So
is it obvious that this thing converges?
No. Yeah, it's not obvious. Actually, it turns out that when you look at the sort of denominator of this rational function, it's actually like very comparable to the dimension of this. I think it's a sum over terms which are like the same degree. The number of terms in the denominator is it's a product of linear forms, which the number of them is equal to the dimension of this. So you have to show some kind of cancellation among those sums
Okay.
to get the required convergence. It's not easy. But it's fairly, I don't know, the examples that I've worked out for like simple toric varieties, just to see what this looked like, you could actually write down the integral and compute it.
Oh.
An example where it's like for a quadratic Severi-Brouwer variety, you can write it down and it's like 2 log 2 something. So you can write it down.
So under your bijection, there's like this, the simplest, the smallest cyclic cubic has discriminant 81, right? And generated by a root of some very simple x cubed plus x plus 1. Well, what does that correspond to? Q squared minus 3?
1 second, I actually have a table. I don't think the smallest one is discriminant 81,
Or maybe this.
but it has to have trace 1 though.
Oh, sorry, I was talking about the field.
Oh, the field, sorry.
But I was wondering if there's something generating that field. What in Q squared minus 3 produces an element in that field?
Well, I'll show you. I don't know these fields that well off the top of my head, but I can show you a bunch of data and I have a table here. So yeah, it's something that we could definitely compute.
Any other questions? Not, let's take